Hello viewers, in today's session we are going to discuss another important and very conceptual problem from definite integrals, right? And in this session we are going to discuss this problem where we are given a function f from closed interval 0 comma 5 to the set of real numbers, and this function f is given to be continuous, right? And moreover we are given that the value of the function f at x is equal to 1, that is f of 1 is equal to 3, and we are given another function phi of x, which is defined as phi of x is equal to integral 1 to x t cube g of t dt, where g of t is defined by this expression, that is g of t is equal to integral 1 to t f of u du. Then we have to find out the value of phi double prime of 1. So viewers, let us see how easily we can solve this problem by using a simple concept from definite integrals, right? See, we know from the theory of definite integrals that if we have a function, say capital f of x is given by the integral a to x f of t dt, then if we differentiate f of x with respect to x, then we get f prime of x is equal to f of x, right? So this is a famous theorem in definite integrals. If we are given a function capital f of x is equal to the integral a to x f of t dt, then the derivative of f of x, that is f prime of x, is equal to the function f of x, right? So here we are going to utilize this concept, and moreover here we can also use the concept of derivative. So now let us start with this function phi of x. So we are given phi of x is equal to integral 1 to x, and here we have t cube g of t and dt, right? So let us differentiate both sides with respect to x and using this concept. So now let us compare this integral with this one. So here we have x, here also we have x, and here we have 1, here we have a. So a can be taken as 1, and this function can be taken as f of t. So f of t is t cube g of t. So if we differentiate both sides with respect to x, then due to this result, we can get phi prime of x is equal to f of x, right? And here we have f of t, so this is f of x, and f of x can now be written by replacing this t by x. So we have here x cube, and then we have g of x. So we have obtained the derivative of phi of x. Now let us differentiate both sides again with respect to x. So now we have phi double prime of x, and here we have d by dx of x cube, and here we have g of x. Now in order to differentiate this function, we can see that this is the product of two functions, right? So using the product rule, so here this function x cube can be taken as u, and g of x can be taken as v. So we have first function, that is x cube, then the derivative of g of x, and then we have g of x and derivative of x cube, right? So phi double prime of x is now x cube, and the derivative of g of x can be written as g prime of x, and here we have g of x, and the derivative of x cube is 3x square, right? So now we have obtained the expression for the second derivative of phi of x. Now we have to find out the value of phi double prime of 1. So replacing this x by 1, we can now write phi double prime of 1 is equal to 1 cube, taking x is equal to 1 in this expression. And here we have g prime of 1, then we have g of 1, and here we have 3 times 1 square, right? So 1 cube is 1, and we are left with g prime of 1, and here this is also 1, so we have 3 times of g of 1, right? So to get the value of phi double prime of 1, we need to find out g prime of 1 and g of 1. So now consider this function g of t. So we have g of t is equal to 1 to t, and here we have f of u and du, right? And again, if we differentiate both sides with respect to t, then we can get g prime of t is equal to f of t, again using this result, right? Here we have f of x, here we have g of t, and then the integral a to x, here we have 1 to t f of u du. So differentiating both sides with respect to t, g prime of t is equal to f of t, right? Now see here, t is a dummy variable, so we can replace this t by x also. So we can now write g prime of x is equal to f of x, right? And here we have g prime of 1. So if we replace x by 1, then we have g prime of 1 is equal to f of 1, right? Taking x is equal to 1 in this expression. So g prime of 1 is equal to f of 1, and from here we can see that in the given problem we are given the value of f of 1 as 3. So here we can take 3. So g prime of 1 is equal to 3. So here we can replace g prime of 1 by 3, and then here we have 3 times g of 1, right? So now we need to find out the value of g of 1. So again, taking the help of this expression, we can find the value of g of 1. Now see, if we replace this t by 1, right? Or before replacing this t by 1, we can also write this function as g of x is equal to the integral 1 to x and f of u and du, right? So if we take x by 1, or replacing x by 1, we have g of 1 is equal to integral 1 to 1, taking x is equal to 1. Here we have f of u du. Now we can see that both the limits of integration are same or identical, so the value of this integral must be equal to 0, right? So g of 1 is equal to 0. So here for g of 1 we have 0. So now this is 3 plus 0, that is equal to 3, right? So the value of phi double prime of 1 is equal to 3. So viewers, this is how we can easily solve these kind of problems using this concept. Hello viewers, in today's session we are going to discuss another important and conceptual problem from definite integrals, and in this class we are going to discuss this problem using the concept of Leibniz integral rule, right? So here we have a function f which satisfies this equation. that is integral 1 over e square to x square f of t divided by t dt is equal to the integral 1 over e to x and t natural log of t dt, where x is greater than 0, right? And we have to find the value of f of e, and we have to show that f has a minimum at x is equal to 1 over e. So here our prime objective is to find out the form of the function that is f of x, right? So once we get f of x, we can easily find out the value of f of e, where e is the exponential number, by taking x is equal to e in f of x, and then using the function f of x and using the concept of second derivative test for maxima and minima, we can show that the function f of x has minimum at x is equal to 1 over e. So let us first quickly see the statement of Leibniz integral rule. So Leibniz integral rule says that the derivative of the integral that is say f of x comma t dt, when the limits of integration are functions of x. Suppose the lower limit is u of x and the upper limit is v of x, right? So Leibniz integral rule says that if we wish to differentiate this integral with respect to x, when we have the integrand f of x comma t and the limits of integration are functions of x, then the derivative of this integral is given by f of x comma, first we replace this t by the upper limit. So here we have v of x, and then we multiply this term with the derivative of v of x, that is v prime of x. Then we have the negative sign, then we have f of x comma, then we replace this t by u of x. So here we have u of x multiplied with the derivative of u of x, that is u prime of x, and then we have here a third term which is the partial derivative of this function with respect to x, right? So we write here integral u x to v of x, and here we have del over del x of f of x comma t dt. So this statement is known as Leibniz integral rule. So now let us consider a special case of Leibniz integral rule when the lower limit is a constant, right? Now see, here we have two integrals, and here the lower limit is 1 over e square, which is a constant, and here also we have the lower limit 1 over e, and this is also a constant. So when we have the lower limit as a constant and the upper limit is some function of x, and moreover here f of x comma t, this is a mixed function of x and t. But if we have here only a function of t, then let us see how this Leibniz integral rule can be modified. So when u of x is a constant, say c, then we can see that this term is going to be 0, right? Because the derivative of a constant is 0. So this entire term is 0 when the lower limit is a constant, right? And moreover here we have the partial derivative of f of x comma t with respect to x, and here we can see that we have f of t over t, which is a function of t only, and here also we have a function of t only, right? So whenever this function is a function of t only, then the partial derivative must be equal to 0. So in that case, this term is also going to be 0, right? So we are left with only this term, right? So we can now write the modified form of Leibniz integral rule using these restrictions. The modified form can be written as d by dx of the integral. Here for u of x we have c, here we have v of x, and then here we have a function of t only, right? And here we have dt. So we are left with only this term. So we can now write f of x comma vx as simply f of v of x, and then multiplied with the derivative of v of x, that is v prime of x. So now we are going to use this result in our given problem. So we'll now take the derivative of both sides. So now we have d by dx of the integral 1 over e square. Here we have x square f of t over t dt, and then we have d by dx of the integral 1 over e to x and t times natural log of t dt, right? So using this result, this is a constant, so we'll simply replace these two t's by x square. So we have f of x square over x square, and then we take the derivative of v of x. So here v of x is x square, so the derivative of x square is 2x, right? So what we have done here, using this result, we have replaced t by v of x. So here we have these two t's, so replacing these two t's by x square and then taking the derivative of x square. And similar is the case with this integral. Here I will replace these two t's by x, so we have x natural log of x, and then I will take the derivative of x with respect to x, that is equal to 1. So now simplifying it, here we have already assumed that x is greater than 0. So we can cancel this x with this one, and we have now f of x square, that is 2 times f of x square over x, that is equal to x times natural log of x. So f of x square is now equal to x square over 2 natural log of x. Now this is a functional equation, and here the input is x square, right? So replacing this x square by other variables, say y, it implies that we are replacing x by square root of y, right? So here we have f of y, because x square is being replaced by y, and here we have for x square we have y over 2 and natural log of x. X is square root of y, right? Now we can write y over 2, and this is natural log of y raised to half, and using the properties of log, we can now write f of y is equal to y over 2 times half natural log of y, that is y over 4 times natural log of y. So f of y is given by y over 4 times natural log of y. So now again replacing y by the variable x, because this is a dummy variable, so we can now write f of x is equal to x over 4 times natural log of x. So this is our function f of x, where x is greater than 0. So now our function f of x is x over 4 times natural log of x, and taking x is equal to e, we can find out the value of f of e. So f of e is equal to e over 4 times natural log of e, and natural log of e is equal to 1. So we have e raised to e over 4 times 1, that is e over 4. So this is the value of f of e. Now we have to show that f has a minimum at x is equal to e. So for this, let us differentiate f of x. So we have f prime of x is equal to 1 over 4 and d by dx of x times natural log of x. So here using the product rule, we have x, then the derivative of natural log of x is 1 over x, then we have natural log of x and derivative of x is 1. So here x and x get cancelled, so we have 1 over 4, 1 plus natural log of x. So this is the derivative of f of x. Let us find out the second derivative. So the second derivative is given by d by dx of 1 plus natural log of x, right? So we have 1 over 4 and the derivative of 1 is 0 and the derivative of natural log of x is 1 over x. So here we have 1 over 4 times x. So now for maxima and minima, the derivative f prime of x should be equal to 0, right? So in order to get the critical points or the turning points, we take the derivative equal to 0. So f prime of x is equal to 0 and f prime of x is 1 over 4 and 1 plus natural log of x is equal to 0. So from here we have 1 plus natural log of x is equal to 0. So natural log of x is equal to minus 1 and this is equal to minus natural log of e, because natural log of e is 1. And here we can now write natural log of e raised to minus 1, that is natural log of 1 over e, right? So natural log of x is equal to natural log of 1 over e, and from this equation we have x is equal to 1 over e. So this is our here critical point or the turning point, and let us substitute x is equal to 1 over e in the second derivative, that is second order derivative. So we have f double prime of 1 over e is equal to 1 over 4 times 1 over e. So this is e over 4. So e is positive, 4 is positive, so the second order derivative is greater than 0, right? So when the second order derivative is positive or greater than 0, then the function is said to have a minimum, right? So we can see that x is equal to 1 over e is a point of minima, and the minimum value of f of x can be obtained by taking x is equal to 1 over e in this relation. So we have f of 1 over e is equal to 1 over e divided by 4, and this is natural log of 1 over e, right? So this is 1 over 4 times e, and this is natural log of e raised to minus 1. So f of 1 over e is equal to minus 1 over 4e, and natural log of e is 1. So this is minus 1 over 4 times e. So this is the minimum value of the function f of x, and the minimum occurs at x is equal to 1 over e. So this is how we can solve this important problem.